In the last video, we learned that rigid body velocities can be represented as a 6-vector twist. The twist can be represented in any arbitrary frame. For example, the twist could be represented as VA in frame A or as VB in frame B. If we want to change the frame of representation of a twist, it is tempting to try a subscript cancellation rule, VA equals TAB times VB, but this doesn't work due to dimension mismatch. Transformation matrices are 4 by 4, but twists are 6 vectors. It is apparent that we need to pre-multiply VB by a 6 by 6 matrix. The 6 by 6 matrix we need is called the adjoint representation of a transformation matrix, and it is defined as you see here. Now we can apply a modified version of our subscript cancellation rule to change the frame of representation of a twist. By analogy to the matrix representation of angular velocity, we would like to find a matrix representation for twists. Recall that for angular velocities, we had the 3 by 3 skew-symmetric matrix representations of angular velocities, bracket omega b equals r inverse times r dot, and bracket omega s equals r dot times r inverse. Similarly, if T represents the body frame B in the space frame S, we have 4 by 4 matrix representations of the twists. Bracket VB equals T inverse times T dot, and bracket Vs equals T dot times T inverse, where little SE3 is the space of 4 by 4 matrix representations of twists. Little SE3 gets its name from its relationship with big SE3. The top left 3 by 3 submatrix is the skew-symmetric matrix representation of the angular velocity, as we've seen before. And the top right 3 by 1 vector is the linear velocity of a point at the origin of the frame, expressed in that frame. The bottom row is 4 zeros. Notice that we are overloading the bracket notation. In one case, it means the matrix representation of an angular velocity, and in this case, it means the matrix representation of a twist. These matrix representations will be used in the next video when we develop the matrix exponential and log for rigid body motions, analogous to the matrix exponential and log for rotations that we've already seen.